think there's many things that are interesting about the world of math. One thing is that the same vocab word can come to mean many different things. So we now have a new word for cylinder. A cylinder is a surface that consists of all lines called rulings that are parallel to a line. So it's going to be a whole set of lines that are parallel to a line that pass through a given plane curve. What's a plane curve going to be? Anybody want to take a guess what a plane curve is going to be?
Oh, cross section?
Well, what's a plane?
A set of all.
Yeah, here's a plane, right? A plane curve would be something you get by taking a plane and doing what to it?
Bending it.
Bending it in a certain way, though.
In a smooth way.
In a smooth way. That's a really good word. That is a legitimate. It's in a smooth way. Like, is this a plane curve? These are all plane curves because you could completely. I'm talking. You could completely describe this plane by what? With a set of lines that are all what? All the lines. You could describe every line here. You could describe this surface in such a way that all the lines are parallel. If I were to like tear this or do something really weird to it, no. The point is by definition, can I do any non-smooth operations on this piece of paper? No, not by definition. If I had some putty, like imagine this was elastic and I like stretched some holes in it, would that be a plane curve? No. So as long as I'm not warping it, does that make sense? Kind of, maybe, sort of? Okay. So for those of you that took notes on this, what are we going to be doing with these cylinders?
Memorize the equations for it.
Yeah, that's a valid thought you could have. There was a table I think they give you on page 836, I think. What kind of feelings does that elicit? That kind of table?
It just looks like shells.
It's complete red.
Okay, it's total dread. I will not have you memorize that.
Yes.
That is too inane. That's too much. Because in order to make those useful, yes, you will do some algebraic manipulation and try to press something into one of these forms. You will have this as reference, or I will specifically say, like, prove that this is an ellipsoid, and here is the general form of an ellipsoid. This is too much. I don't see this as being much purpose. But what I do need you to understand is what these families of functions are. Like how they relate to each other. Like when do you get a cone? When do you get an elliptic paraboloid? Of those 6, which one do you think is my favorite?
Ellipsoid?
Nope.
The saddle one.
Yeah, the saddle one. Do you know what that's called?
Yeah, hyperbolic something.
Parabolic hyperboloid?
You just reversed it. That's right. Hyperbolic paraboloid. Yes. Okay. So, for example, here, plane curve right here. Here is a parabolic cylinder. It's a cylinder because it can be made up, the entire surface can be made up of lines that are all parallel. And you can see them, they're drawn in. Each of those lines, each of these lines, these are called what? These lines are called? Rulings. These lines are called rulings. Now here's the thing. Is y in this equation? No. So that equation is independent of y. So if you pick one y value and draw the answer, and then you pick another y value, you can draw it, and then what do you do with that shape? Is equal? Yeah, it's a parabola, and what are you doing? You're shifting it, right? You're shifting this parabola along the y-axis. Could we make this parabola go up? Could we make it come at us? Absolutely. Could we make it go along the x-axis? If we wanted to make this go along the x-axis, what equation would it be? Y equals... Really? Which one is it? If I want, I'll draw it for you. I'm sorry. I'll make this more clear. If I wanted to do this, let's say here's my axes right here. There's the origin. Yes, I haven't drawn it, but you're correct. I want to do this one right here. I want to do this one. Yes. Do you agree that this is z equals y squared? Yeah. And it passes this way. Hey, that's not bad. Yeah, it's not bad. You get good at it. Basically, you just have to do it without thought. You just do it. So that's z equals y squared. Okay, that's pretty cool. Yeah, go ahead.
Just can you change the grid on the...
I will give this to you as being also not cool. And you'll notice anything not cool is marked with yay.
Isn't that a quadratic surface, not a
It's a quartic. That's how it's what it's called. It's just
Isn't it quartic 4?
Yeah, you think it's 4. I want to check that. As far as I remember that it is quadratic. Quadric. I made a typo right there. It's a very good catch there. I've always thought it's been quadratic. It is a quadric. You're absolutely right. Good job.
Like, is it, I thought
Yeah,
it
it is 4. It is 4.
Quadratic.
I mean, I also thought that a cylinder looked different than this. You know, I mean, there's different definitions for the same word. I mean,
So is cylinder kind of like a rectangle, where a square can be a rectangle, but
kind of, but in this case, we're is this a closed shape? Does this like close in on itself? No, it doesn't. I mean, the tradition, like we have to evacuate some past definitions. Okay, we're back to here. This is a surface of a secondary equation in 3 variables. This represents any possible pairing, right? Any possible pairing in this classification. Now, in your book, there's a really cool place where I want to find the exact words they use here. They give you, at the bottom of page 833, they give you this quadric surface right here. They say this is a quadric surface. And then they have this magical line. They say, but at the top of page 834, it's a little story time here. It says, but by translation and rotation, it can be brought into one of 2 standard forms. So what they're saying is this nasty thing, this entire family of surfaces, you can distill them down to a smaller equation. Let me paste it in there to show you what I mean. Essentially. Now, what's interesting is in any math book, they lie or they omit certain things. They don't say, you can omit something and say, like, we won't show you this here, but we need to show you later. Or sometimes they say things like, this can't be factored. Is there any polynomial that can't be factored? No, every polynomial can be factored. But when you're in Algebra 1 or Algebra 2, you're only looking at factoring with integers, right? Integer coefficients. So they say things like, you can't factor this. Well, in this case, there's a magical step here where they start with this nasty, huge thing and say, well, by translation and rotation, you can actually bring it all the way down to one of these 2 families right here. Now, here's the thing. Do they even mention that there's a proof for this? Do you understand when I say a rigid transformation? If I put this book in space and I don't change the overall shape of it, but I move it over here, is this a congruent 3-dimensional shape?
yes.
What they're saying is that all of these shapes that fit this top form right here can be actually written in this form if you just take away, like this shape is the exact same thing as this. So if you took all the possible shapes here and basically like squared them off, you would limit it to this form of equation. Now here's the thing. Does the book even mention that there's some math behind that? No, they just say, by translation. Are translations a pretty nasty form of math?
Yes.
Yeah, moving stuff around can be really nasty. What I mean by that is this. Let's do something really simple, just to get you to think about something geometrically really simple. You know what this looks like, right? Y equals x squared? Yeah, y equals x squared. We have y equals x squared. It looks like this. Nice, right? Okay, so I want you to put a pin right here at the origin and spin this, I don't know, 17 degrees around the origin. Write a relationship for the new shape. You understand what I'm asking, right? You just like turn your head 17 degrees, right? Does it suddenly change it into a much harder question?
Yes.
Yeah, it does. No, I don't know how to. I mean, you'd have to. My guess is you have to translate it into some other coordinate system. You would write y equals x squared in a different coordinate system. Like polar graphing can attune for shifting. I think I've never really thought about this, but is this something that's easy to do in Cartesian algebra and geometry? No, not at all. Not at all. It's terrible. It is terrible. First method is with a computer, like an algebra system. They call them computer algebra systems. You saw it with a computer.
Like the 89 can do it.
Yeah, the 88, the 92s can do it.
89 and 92 are the same thing, just without a keyboard.
Yeah. And then 2, by hand, how are we going to do it? What did you say, Josh?
Traces.
By traces, exactly. So, has anybody ever seen the what's the proper name? The human body exhibition where they take human bodies and they've sliced them and then they've also like removed the skin and so you can see what it looks like. They've preserved them. Body works. Yeah, that's right. I think that's what it's called. Daniel and Jay. Yeah, you're gonna do the same thing. So if you had, for example, this. Let's get that picture. Where's the hyperbolic paraboloid? I have it in there somewhere. I really like the hyperbolic paraboloid. There it is. It's a cool shape. I think it's a pretty neat one. What point are we going to focus in on the hyperbolic The saddle point. That's right. It's kind of cool. How are we going to go by graphing something like that? Well, let's say I had that 3-dimensional shape. You can think about the BodyWorks exhibitions where they took a human body and they sliced it, really, really thin slices, and then like spread them apart and then put them back together. It's pretty neat stuff. We're going to do the same thing. We're going to take surfaces and we're going to cut them along certain planes. Like we're going to cut it like this, and what are we going to look at? We're going to look at where this plane does what? Intersects that plane. So we're going to draw the trace. We're going to draw the trace, and then we're going to maybe connect the trace. Are we going to be able to draw super accurate graphs using this method? No, we're not. We're going to get general things like, is it a cone? Is it a hyperbolic paraboloid? Is it an ellipsoid? Is it an elliptical paraboloid? Is it a hyperbolic of two-sheet? That's the kind of thing we're looking for here. Am I looking for exactness? Like, are you going to be calculating intersections based on three-dimensional planar surface graphs? No. No, not at all. Not unless you're using mathematical. And then Mathematica wouldn't even be doing it that way. Mathematica would actually be using computer algebra to calculate intersections, which is smart enough to do. What's one thing you could notice about this? What's one thing, Josh?
Is that z is not squared?
Yeah, mentioned z is not squared. That's a really good thing to notice. Okay. So let's say I started with this. If z is 0, what does x and y? What do x and y have to be?
0, 0.
Yeah, they really. So you know this thing hits the origin. That's right.
And nothing else will be 0.
Yes, that's correct. Okay, what happens if x is 0?
Then y.
If x is 0, then you have z is equal to y squared. Z is equal to y squared. So what's that going to look like? So when x is 0, where is x 0? Yeah, so here's x, here's z, and here's y, right? So x is 0 on this plane right here, right? Everybody see that? So when x is 0, we have z equals y squared. And I just drew the wrong plane. Gotta stop me. I meant to draw this plane right here. Thank you. So what can I draw on this plane? A parabola. Yeah. So you know it's going to go up like this on that plane, right? Okay, that's nice. Great. What happens when y is 0? Z is equal to 4x squared. So what kind of parabola is that compared to the one we just drew? It's a different plane, and it's steeper. It's a bunch steeper. So we're going to go upwardly steep along that plane. So do you have a basic idea of what it looks like now?
It's going to be like, yeah.
Yeah, let's draw some traces. We have to be careful about this. Yeah, a weird bowl. I like that. That's good. There's a proper name for this. Do you remember what it's called in your notes?
Elliptic paraboloid.
Yeah, there's all these really practical terms you're going to need later in life, right? This is called a elliptic paraboloid. You like this stuff? Paraboloid. Awesome. Is that pretty cool? Yeah. I mean, it's basically by investigation. Yes, Gately.
Could you,
Kids, sit down. Understand how, if I can actually write it, how to graph these by hand. That's the first part. Okay, we're going to go on a little bit further. So we've had a lot of shape drawing. Let's do something more algebraic. Sound fun? Yay! Cylindrical coordinate systems. All right. So here's the cylindrical coordinate system right here. It's another way to describe a point in 3 space. So instead of having the x, the y, and the z coordinate, shut your laptop, please.
Yeah.
You will have theta being defined as the angle from the x-axis, r being the distance from the origin to the shadow directly below the point, or above it, depending if it's above or below the xy plane, and then z being the height. In this case, if I was going to write this, I can write this in cylindrical format, or I could write it in, what was our first coordinate system called?
Cartesian.
We're not really... Did we have a name for it? Was it Cartesian?
free space
Rectangular.
with
Rectangular coordinate system. Rectangular coordinate system. What coordinates stayed the same?
Z.
Z stayed the same. So x and y have been replaced with theta and r. Theta and r. Absolutely. So algebraically, what does this mean? You get these very, 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 very helpful relationships.
Is something we should memorize?
Absolutely. You can also figure them out yourselves. To convert from cylindrical to rectangular, x is equal to r cosine theta, and y is equal to r sine theta. You can see that pretty clearly by looking at this triangle right here. In rectangular coordinate line, that would be x, and then this would be y. You also know that x squared plus y squared is r squared, and tangent theta is y over x, and z is equal to z. Do you understand the basic mechanics here? So if you have a point in space, you just need to find the theta value, the r value, and then you can go from rectangular to cylindrical. Now, just because they don't like to stop there, there's one more here. I'll zoom further in. Spherical coordinates. Anybody, you guys had to take notes on this, so this shouldn't be too new to you. The biggest question is, what are the words they use to describe each of these Greek letters? Okay, so there's our point P in space. Yay! Now there's nothing in common with rectangular coordinates. But what's the one thing that's in common with cylindrical coordinates?
Theta.
Theta stays the same. Rho, in this case, which one's rho? The P
Or
thing.
The last one.
Yeah, you pronounce that rho. Rho is the distance from the origin to the coordinate.
Kind of like R.
Kind of like r, except r in this case is right here, right there. How do you pronounce this right here?
Duh.
Anybody know? It's phi. Anybody remember? Kind of, maybe, sort of. Physics, phi. Yeah. So in this case, you can think of it as a gun. You're shooting. It starts laid down on the x-axis. You then have to rotate a certain amount on the xy plane, and then you have to go up a certain amount. In this case, they measure it from a down angle from the z-axis. And then rho is just the distance you're firing in space. Does this seem a little overwhelming? Maybe. The algebra can get pretty nasty. At this point, right now, the only thing I want you to understand two things. Well, understand one thing and be comfortable, even though you haven't done it yet, doing one other thing. First thing, I want you to be comfortable understanding, at least I want you to understand how to describe a coordinate in each of these rectangular, cylindrical, and spherical coordinate systems. What's the first thing you need to be able to do if you're going to work with these three things? Convert between the two. Is there a nice conversion table for this right here?
Yeah.
Oh yeah, absolutely. It's more complicated, but it's not that bad. So you end up with this right here, and I can clip this in for you. You can put everything back to rectangular coordinates. Z is equal to rho cosine phi, and R is equal to rho sine phi. Also, X is equal to R cosine theta, and Y blah, blah, blah. What's the easiest kind of mistake to make when you're working with these three coordinate systems?
Cosine and sine.
Switching trig values, sure, but what else?
Switching the theta.
Why would you switch? Yeah, why would you switch theta and phi, for example?
Because they look the same.
They look the same, so therefore if you're writing a whole lot of these, what could happen? You could just make a careless mistake. Make a mistake of organization, like put the line the wrong way, and then all of a sudden, boom! Is your life harder all of a sudden? Yeah, it is. So, numbers you could take away from this.
Write your C's and thetas carefully.
Yeah, be careful. A lot of this folds nicely together. Now, here's the big question. Why do we have different coordinate systems? Yeah.
It's much easier to like manipulate the equation in cylindrical for like spheres and shapes that are around the same.
Certain shapes lend themselves to manipulation in a much more clear fashion when the shape, surface, solid is written using a specific coordinate system. So let's look at these for a second. So we have cylindrical, we have spherical. Let's talk about spherical first. What kinds of shapes would spherical coordinates be easiest to work with? What kinds of shapes? How would you describe them, Gately?
Spheres, cones, anything that, like,
Things that have
revolves around a point.
revolves around a point. If it revolves around a point, spherical, nice. What about cylindrical?
Revolves on a line.
Cylinder.
Revolves around a line, exactly. Rotational volumes will be vastly simplified. So it might be harder to set up. It might be this much harder to set up, but then how is the integration? Really easy. The integration becomes much easier, but the setup might be a little bit more tricky. Yes.
So what happens when you start squaring?
Recording now. So what's x equal to? What's sine of pi over 3? Root 3 over 2. What's cosine of pi over 4? Exactly. So in this case, what's the answer going to be? Root 6 over 2. We'll take this, we'll move it down. I know I'm cramping this together, and I know that's a bad faux pas, but deal. So we end up with 2 times root 3 over 2 times sine of root 2 over, oh yeah, the sign goes away when you actually evaluate the sign. Yeah, that's true, Mr. Seaman. So you end up with what? The same thing. Yep. Come on, there you go. And then what do you end up with here?
1.
2 times, which is 1. So can you now plot this using rectangular coordinates? Absolutely. So it's basically just what? Plug and chug. That's all it is at the moment. So the first things you have to do in order to use this coordinate system is understand how to move between them. Are we going to do anything complicated with them yet? No, absolutely not. We're gonna move between them and do some basic questions. Basic questions. So you need to be able to graph these by hand and work in these 2 basic operations. You're learning the variables, you're learning the vowels, you're learning the consonants. We haven't really formed any sentences yet with these coordinate systems. Do you understand what I'm saying? You need to learn how to do the basic manipulations, and then you can do the fun stuff. Got it? Sound good?
Like 3 conversion things.